Good evening. Am I audible? Will you please let me know? Okay, thanks. So we'll start our discussion on those topics: polar plot, Nyquist plot, gain margin, phase margin. From control system, we'll discuss few problems. I think student may join later, but we can start. We can give you some brief introduction about those topics. Then we'll discuss few problems from GATE papers. Now, simply the polar plots. As you know that, okay, let me consider this one. So in control system, you will find this kind of system, that there is one plant, that is ES, and it is having one feedback. That function is h of s, and generally it is a negative feedback. This is plus, this is minus, and this will call it reference input Rs, and that will call it controlled output Cs. And we understand that this Cs equals to Gs or Cs upon Rs. The transfer function is given by Gs upon 1 plus Gs Hs. And stability depends on the pole position. If all the poles are, so if I consider this closed loop transfer function, and this is your right hand side of S-plane, real part, this is your imaginary part. If all poles will lie on this side, then only it is stable. If we find any pole on right hand side of the S-plane, closed loop pole, then it will become unstable. So how to find the poles? So this denominator 1 plus GSHS, that will make it 0. We'll solve for this equation, that will give you the pole positions. Okay, so I'll take very few minutes only, 1-2 minutes, to discuss the basic concept of polar plot, Nyquist plot, gain margin and phase margin. Okay, then we'll discuss the problems. So these poles we can find out. Now here we'll use polar plot, Nyquist plot to understand the stability of the system. So in polar plot, what you will do, so here we will consider, so Gs is given. In the Gs, first we replace S by j omega, we will get G of j omega, and this G of j omega will have one magnitude and one angle or phase, right? So if we plot this thing with respect to frequency, then we will call it polar plot. So this gain function G of S, how it is varying with respect to frequency. So with one example, briefly I am discussing, okay? So Gs equals to 1 upon S into S plus 1. So what is the polar plot? Polar plot, so this magnitude and phase both. So generally for different frequencies we can find out magnitude and phase. So omega, we can find magnitude, we can find phase. Okay, So omega equals to 0 and omega equals to infinity, at least these two, and some other intermediate omega we will consider later. So with omega equal to 0. So what is the magnitude here for this function m? So you can understand that this one is simply 1 upon j omega, and it is j omega plus 1, right? So what is the magnitude? 1 upon omega times square root omega square plus 1 square means 1. And what is the phase? Phase is, so the 1j in denominator will give you minus 90 degree, and this another pole will give you minus tan inverse omega by 1. Okay. So you can note that as there is one pole at the origin, it will start from minus 90 degree, and at omega equal to infinity, total phase will be minus 180 degree, and magnitude will become, so you can see that at m equals to, so at omega equal to 0, m equals to infinity, and phase will be minus 90 degree, and when omega equals to infinity, magnitude will become 0 and phase will become minus 180 degree. So in between it will vary, so magnitude is reducing and phase is moving towards minus 180 degree. So plot could be like this, okay, this side. So it will start from minus, this is angle is minus 90 degree, this is your 0 degree, this is your minus 180 degree. Okay, that angle we will consider. So this is the polar plot, that's simple. So one pole means it will start from minus 90, two pole at origin, pole at origin only, okay. And if you have two poles at origin, it will start from minus 180 degree like that. So we will discuss more problems. I hope you have certain ideas, but here we are discussing very briefly, right? Now, what is the gain margin, phase margin and Nyquist plot? So in Nyquist plot, what we will do, or first I can consider this gain margin and phase margin also, right? So in Nyquist plot, how to compute Nyquist plot? First, you will consider GS-HS plane. So this is your GS-HS plane, its real axis, its imaginary axis. Here you will put all the poles and zeros on this S plane, GS-HS plane. Okay, that you can do, or simply first we can start with only S plane, rather, okay, not only this one. First we will consider S plane. There we will put these things. Suppose we will take one example. So GS-HS, it is given as, suppose 2 times S into S plus 1. Okay. So first you consider the open loop poles and zeros. So what is the poles? I have one pole here and one pole at minus 1. So what I will consider, I will do, I will consider a contour to cover entire right hand side. Okay, like this. But we should bypass this pole if it is there on the imaginary axis. Now it is an origin at origin, so I need to take a bypass line, this one. Okay, so we are getting this one. So here you will consider few lines. So this is the on imaginary axis. I will consider this is L1 and this one section is L2. This could be L3. This could be L4. That kind of section I can consider. Okay. Then what you will do? You will map. You will consider polar plot for this GS-HS. For this L1 section, L2 section, L4 section, everything. Okay. So Now if I do the polar plot for this one, what you will get? So very briefly, I am hoping that you are having some concept on Nyquist plot. If you don't have any concept on Nyquist plot, you can't understand. Okay, this is not for basics. So if you have some understanding on Nyquist plot, you can follow me and you can solve few problems. Now this, what I'll do, I'll go for polar plot. Already I said that what will be the polar plot for these things, for this L1 section. So L1 section is looking like this. So L3 and L1, this is the mirror image. You will just simply consider just opposite of this one. And if you have one pole at origin, what you will do? You will consider a semicircle this side. Okay. Then think about minus this one point, minus 1 plus j0 point. Okay. So how many times this contour will enclose this minus 1 plus j0 point? That is your capital N, but it should be in anti-clockwise. How many times it will enclose this minus 1 j0 times anti-clockwise? That is your capital N. Okay. So N is number of times it will enclose minus 1 plus j0 point in anti-clockwise. And then we'll consider number of open loop poles on right hand side within this contour, that is your P. And then we'll consider number of closed loop poles, that is your Z I'll consider, or modified zeros. So P minus Z, that will give you N. So simply I am saying that N is number of times this contour will enclose minus 1 j0 point in anti-clockwise. P is the open loop poles. So in this case, you see there is no pole, so P is equals to 0. And N, how many times it will enclose? No time, so it is not enclosing, it is outside this one, so N equal to 0. So you replace this 2, so N equal to 0, P equal to 0, you will find Z, and if Z equals to 0, then only it is stable. So in this case, this system is stable. Okay, I think you have got this concept. I will solve few problems. Okay, now what is the gain margin and phase margin? That I will discuss along with the problem. Okay, so let me start with the problems. So this is the first problem. So can you solve this one? So I will go for the figure 1. So can you solve this problem? Anybody? Can you try? Okay, anybody? So how will attack this problem? So this problem, it appeared in GATE 2001. It's not that much difficult to solve it, very easy things. So here I will give you some idea how to solve it quickly, but if it is for your semester purpose, you need to solve it thoroughly. Okay. So number of poles on right hand side, that we need to decide. So what we will do? First we need to understand how many times this contour on GS plane will enclose -1 plus j0 point. Okay, so in this case, how to find it? We'll consider this point. You can see that one time it is clockwise manner and another time it is anti-clockwise manner. Okay, so total number of rotation would be, for anti-clockwise +1, for clockwise it is -1. So total n will be +1 and -1 equals to 0. Okay, but this is not enclosing. This circle is not enclosing the -1 j0 point. Okay, the big circle and right side small circle. So this n equals to capital N equals to 0, and it is already said that G has no pole on the right hand side. Okay, so this is equals to 0. So as G has no pole on right hand side, so capital P is also 0. Is it okay? So if capital P is 0, now we'll compute simple thing, n equals to P minus Z, n equals to 0 and P equals to 0, so it is Z. If you solve it, Z equals to 0. It's very simple. So if Nyquist plot is given to you, just decide how many times it will enclose this -1 j0 point, that is your capital N. Compute that one. Okay, then use this equation, n equals to P minus Z. You will get these things. Okay, is it correct? Yes, Joy, you have done correctly. I hope it is very simple thing. So this answer is A. Right. Now we can move to next problem. Now this is about gain margin and phase margin. This problem, can you see? Okay, this is one problem regarding gain margin and phase margin. How to tackle this problem? So let us understand what is gain margin and what is phase margin very quickly. Okay, so what we will do? So already we have seen that in Nyquist plot, main important concept is the polar plot, whether it is enclosing -1 j0 point or not. If yes, I am explaining this. Obviously, you are asking for probably gain margin and phase margin, right? So -1 j0 point is the most crucial point. If the contour is enclosing -1 j0 point, then system is becoming unstable. If open loop system was stable, right? Suppose I am saying that if n equals to 0, sorry, n equals to something, okay, but P is given 0, open loop system is 0, there is no pole, open loop pole is not there on right hand side, so P equals to 0, it is stable. Open loop is stable. Now under closed loop, whether it will stable or not, that we need to decide. So you will see that this n equals to P minus Z. So if P is equal to 0, then it is simply minus Z. So in order to be stable, means Z to be 0. So if n equals to 0, then only it is stable. Otherwise it is unstable. In other words, what I am saying that if open loop system is stable, in the closed loop system, this GS-HS plane, that contours should not enclose minus 1 J0 point. Otherwise it will be unstable. Okay, so that's how this point minus 1 plus J0 point is crucial. Suppose I have this kind of plot, right? So this plot. So I am not drawing entire one. So you can understand that rest part is there, this side is there, and this total circle is there. Okay, just I am considering this part, this one. Okay, in this polar plot you can see that this is not enclosing minus 1 J0 point. Sometimes it could be very close. In that case, okay, we need to find out the margin, how far away it is from this minus 1 J0 point. Okay, now concept is, to get this concept, what I will do, so when it will cross this minus 180 degree axis, at which frequency it will cross, that frequency is called omega p, the phase crossover frequency. At this phase crossover frequency, whatever magnitude is there, if this magnitude is A, correct? If this is the magnitude A, and then you can see that how much gain we can, additional gain we can provide, so that just it will become unstable. Means with this A, how much we will multiply so that it will become 1, because this point will come to this point. So that factor we can calculate. So what is the factor? Obviously it will be 1 upon A. So if A is the magnitude at phase crossover frequency, then we can provide additional gain of 1 upon A, then only it will become just on the verge of instability. Is it clear? Okay, so this is important. So thus the gain margin is 1 upon A. So what you will do? First find the phase crossover frequency. How to find phase crossover frequency? When phase will become 180 degree. When phase is becoming 180 degree, that frequency we need to calculate. That frequency is omega p, the phase crossover frequency. At phase crossover frequency, what is the gain? That gain is suppose A. So gain margin will be 1 upon A. Okay, this is normal scale, or we can consider this is 20 log of 1 upon A, that will be in dB scale. Okay, if we want to convert in dB scale, we need to go for 20 times log of A base 10. Base should be 10. So this is the concept about gain margin. And what about phase margin? Phase margin is similar thing, just only difference is that. So first we can consider one unit circle. So on this unit circle, everywhere you will see that magnitude is 1. So when it will cross this unit circle, that frequency will calculate, we will call it omega g, gain crossover frequency, because at that frequency gain will become 1. So gain crossover frequency is the frequency at which the gain will become 1, that is the omega g. So at omega g, what is the phase? So this phase you find out. Okay, so you can see that it is a little bit far away from minus 180 degree. So what is the gap from minus 180 degree? So phase margin, or PM I can write, PM will be simply 180 degree plus phi. That's all. And phi is something negative. Suppose if phi equals to this phi, for example, it is minus 135 degree, then it will be 180 degree minus 135 degree. It will be 45 degree. Okay, if phase margin is positive, it is stable. If gain margin is more than 1, then it is stable. or in dB scale it is positive, right? That is the important thing. Now can you solve this problem? So how to attack this one, right? So this one, so I need to erase this part. Okay, now can you solve this one? How to solve it? So in this problem we need to find out gain margin. So I need to compute phase crossover frequency first, that is the idea. So what is the phase crossover frequency for this problem? So at that phase crossover frequency, what is the phase that you need to calculate? Then phase margin will be simply 180 degree. Okay, this is the gain margin, sorry. Okay, so at phase crossover frequency, what is the gain? That gain A you will calculate. So gain margin would be simply 1 upon A, right? So can you compute? What is the GSHS? So you are saying 0 dB? Yes, it looks good. I think it will be 0 dB. So how to calculate this thing? Okay, now GSHS. This is 1 upon S into S square plus S plus 1. So first I will consider G of j omega, H of j omega, we replace S by j omega. This is 1 upon j omega and this is j omega square, means j square is minus 1, so minus omega square plus j omega plus 1. I think it is clear. I am replacing S by j omega. So this is the form. Now this is 1 upon j omega and this is your, I can rearrange 1 minus omega square plus j omega. So how to get 180 degree? When the phase will become 180 degree? At which frequency? So you see that I have this kind of problem. So this will give you, what is the phase? Phase will be simply, it is minus 90 degree for this j, and this is the real part, this is the real part, this is the imaginary part. So minus tan inverse omega by 1 minus omega square, right? So it should provide another 90 degree. Why it will provide 90 degree? Because to get 180 degree, so I have already minus 90. So if I have more than minus 90, again more than minus 90, I will have total minus 180 degree. So this should provide minus 90 degree, and tan inverse infinity will give you 90 degree. Okay, so this should become infinite, means something by 0, this should be equal to 0. So 1 minus omega square, it should be equals to 0. That imply omega squared equals to 1, that means omega equal to 1. Is it correct? So at omega equal to 1, the phase will become minus 180 degree. So phase crossover frequency is 1 radian per second. So at 1, what is the magnitude? Now magnitude you can calculate easily. Okay. So can you calculate the magnitude? So what is this? So you can see that G of S was given 1 upon S into S square plus S plus 1. And there we have got this thing, G of j omega is 1 upon j omega, and this is 1 minus omega square plus j omega. So what is the magnitude? So phase crossover frequency I have got it. That is equals to 1 radian per second. So what is the magnitude that time? So magnitude is 1 upon omega square root this real part square plus imaginary part square. Now the A is the magnitude at this phase crossover frequency 1. So I will put omega equal to 1 here. So this is 0 and this is 1. So this is 1 by 1 means 1. So A equals to 1. If A equals to 1, what is the gain margin? Gain margin is 1 upon A. This is 1 upon 1. That means simply 1. Okay. So gain margin 1 implies that it is under critical conditions. If you increase little bit, it will diverge. It will become unstable. No. So this is in normal scale. If I consider dB scale, it is 20 log of 1 and log 1 is 0. It is a 0 dB. So you can see this thing, it is in dB scale it is given. So obviously the answer would be 0 dB. It's correct. Okay. Is it fine? Should I discuss more? Any confusion please? Yes, gain margin is 20 log of gain margin 1 upon A. Exactly. That is fine. Joy, what is your question? I am not getting you. The 20 log of 1 upon A. It's fine. It is 1 upon A, not only A. Don't consider A. It is gain margin. So gain margin is 1 upon A. That's how it will be 20 log of 1 upon A. If A is negative, then only log of 1 upon A will be positive. So if it is a positive dB gain margin, then it is stable, otherwise not stable. So you understand this thing. Okay. If gain margin is more than 0 dB, then that implies it is stable. That same meaning is that if A is less than 1. Okay. Good. So we will go for next problem. So can you solve this one? So look at the problem carefully. Read this one. Yes. So can you solve this problem? So what it is saying? In the figure, the GSHS plane, the contour plot is given. And it is already said that this one, the GSHS has one right hand side pole. Okay. So what is the meaning? What I have said, if right hand side you are having one pole, that time we will consider P equals to 1. One pole on right hand side. So in the S plane we will enclose that right hand side pole. Okay. Now from this GSHS plane, this contour, we need to understand how many times it will enclose the -1 plus j0 point. Right. So this is the point -1 j0 point. So this is the direction it is enclosing. So obviously this one this n equals to so this anticlockwise thing we have considered n equals to positive. So it is one time it is enclosing, so n is equals to also 1. Be careful. Okay. So what is your equation? Equation is that n equals to p minus z, n equals to 1, p equals to 1, it is z, so z equals to 0. What is the meaning? There is no closed loop pole on right hand side, so it is always stable. So this is stable. So this A is correct answer. It is always stable. Now if I say one thing, okay, this system is having only one pole on right hand side. If I say this one, is it correct? There is no zeros, only pole on right hand side. Can I get this kind of polar plot? Can you give one example of that? Anybody? Are you getting my point? What I am saying? This kind of polar plot, kind of polar plot, can I get using only one pole on right hand side? Suppose I'll give you one example. If GSHS is 1 upon S minus 1, what is the polar plot? Alright, not S minus 1, I will put S minus 2. Okay? And here it is, I will put it k. Numerator is simply constant k. So k upon S minus 2. Can you understand? So this is very crucial what I am going to discuss. GSHS is of this form, k upon S minus 2. Can you draw the polar plot for this one? It is very, very crucial. Okay. So let me discuss in detail. It will help you. So GSHS is of the form k upon S minus 2. Okay. So this thing we can write as k upon or minus I can take common minus 1. This is 2 minus S. Okay. And this k, this minus 1 I can write j square. And this is, so now I will consider g of j omega and h of j omega. So I replace that one. So this one will become 2 minus j omega. Is it correct? So what is the phase? The phase is, so numerator there is no zeros, so they will not contribute anything, so 0 degree. So k will provide only 0 degree. J square, 1j is 90 degree. 2 j square means 2 times, so minus 180 degree. And for pole it is minus angle. It is minus 180 degree for j square, 1 upon j square. And this phase is tan inverse minus omega by 2. On that we can write minus tan inverse omega by 2. I will consider omega is positive. Okay. So that is subtracted minus tan inverse omega by 2. So what is this? Minus 180 degree. Okay. Plus tan inverse omega by 2. Now we can see that how phase is changing. So when phase omega equals to 0, that time the phase equals to minus 180 degree. And when omega equals to infinity, phase this will provide 90 degree. So minus 180 plus 90, is minus 90 degree. Okay, so minus 180 to minus 90 it is moving. And what is the magnitude? So magnitude also you can calculate, corresponding magnitude. So magnitude simple, it's the k upon square root 4 plus omega square. Okay, so at omega equal to 0 it is k by 2. At infinity it will become 0. Okay, so what is the polar plot? Right? So can I consider this thing here? So this polar plot, you can see that this magnitude I have got, it's a k upon square root 4 plus omega square, and phase part we have got minus 180 degree, sorry, plus tan inverse omega by 2. So how it will start? So this point at omega equal to 0, I have said that it is minus 180 degree. This is start from k by 2 and it will move to this side because this is minus 90 degree. So what is the important thing I am discussing? This value is k by 2. Okay. So if k by 2 is more than 1, then only it will enclose. Right? Am I correct? If k by 2 is more than 1, I am assuming that it is enclosing. So minus 1, the 0 point is here. So what is the meaning? The k by 2 is more than 1. So that implies that k is more than 2. Okay. Now 1 plus GSHS. What will happen? 1 plus GSHS. So GSHS I have considered k upon s minus 2. So what is this? If I simplify, s minus 2 plus k. So what is happening? S plus, it is your k minus 2 upon s minus 2. Is it okay? Now you can see that what is the modified zeros or closed loop poles. So closed loop poles, the closed loop pole will be at s equals to k minus 2. Am I correct? Is it clear to all of you? Now I am finding the closed loop pole for that system only. Okay. Is it fine? So this is the closed. You can see that if k is more than 2, that we have considered here. So this s value, sorry, it will be your 2 minus k. I think minus sign of that. It is minus, so it is 2 minus k. If k is more than 2, this is negative, means pole will be on left hand side of S plane, so it is stable. Any confusion? Is it clear to all of you? Okay. Any doubt please? No. So let me discuss the next problem. can you find the gain margin of this system? Okay. The system is given by GS equals to S plus 1 upon S square. Okay, so can you solve this problem? Anybody? It's infinity. So how is it infinity? Okay, so it's good. It could be infinite. Why? Because GSHS you can plot it. So what is the plot for this one? So as a square term is there, it will start from this side, and then one 0 is there. 0 will provide positive phase, so ultimately it will go to this side, again similar to that one, previous one, but this is the plot. So again this side I can consider Nyquist plot. So one full cycle will be there. This thing, okay. So in this case -1 J0 point will be here. So you can see that this system is always stable for positive gain k, because how many times it will enclose? So one is clockwise, other one is anti-clockwise. So an equals to 0. Okay, and open loop system is also stable. So means P equals to 0. There is no pole on right hand side. So Z equals to 0. As Z equal to 0, it is always stable. If system is always stable for any k, we will say that margin is infinite. We can provide infinite gain, then also it will remain stable. Okay, so gain margin is close to infinity, because you are not getting the phase crossover frequency again. Okay, here A is not infinity. Don't consider that A is equals to infinity, because at omega to 0 the magnitude is infinite. So you are considering that at phase 180 degree the magnitude will be infinite. So in that case A is infinite and 1 upon A is 0. That is not the case, because here you need to understand the system is stable or not first, because this system is always stable. And you can see that any second order system, so here it is 1 upon I write here. This is 1 plus k times s plus 1 upon s square, that equals to 0. So it will be s square plus ks plus k, that is equals to 0. If you solve this equation, if all the coefficients are positive, then obviously you can expect that roots will be on left hand side of S plane. Could be complex, that does not matter, but system will remain stable. So in second order equation, if all the coefficients are positive, then system is stable. That's all. Okay. Now we will consider the next problem. So can you solve this one? What is the phase margin? That is for GS equals to 10 upon S plus 0.1, S plus 1 and S plus 10. So it is said that gain margin should be calculated using asymptotic Bode plot. So you can understand the Bode plot, all those things. Okay, so let me discuss this one. So we need to calculate phase margin. What I will do, so first I will write the GS. What is the GS? It is a 10 upon S plus 0.1, S plus 1 and S plus 10. First write the GS in this form, 1 plus S upon A, every factors. Okay, so numerator is 10 fine. So what I will do, I will take from this one, I will take 0.1 common. This will become 1 plus S by 0.1. So this is fine, it is 1 plus S. And last one is 10 common, 1 plus S by 10. Okay, so if you simplify this 0.1 and 10 will cancel out. So it will remain same numerator 10, just it is becoming this 1 plus 10s or simply S by 0.1, then 1 plus S and 1 plus S by 10. Okay, this is simple, the GS. Now can you draw the Bode plot for this one? So how to draw the Bode plot? So you can see this one. So GS I write again, it is a 10, 1 plus S by 0.1, 1 plus S and 1 plus S by 10. So these are the corner frequencies. So I will draw both magnitude and phase plot. This is the log omega axis and this is your dB scale, 20 log of m. Okay, so you can see that at omega equals to 0.1 there is a corner frequency, 1 there is another corner frequency and 10 there is another corner frequency. So what is the DC gain is 10. So 20 log of 10 is 20 dB. So up to this one you will have 20 dB. Then you will have a slope of minus 20 dB per decade because of this factor. Then another one from here. Now you will get minus 20 dB, minus 20, minus 40 dB. And from here 60 dB. So this is your slope is minus 20 dB per decade. This one is minus 40 dB per decade, and this one is minus 60 dB per decade. Okay. So what is the gain crossover frequency? Because you need to find out the phase margin. So phase margin means at which frequency the gain will become 1. That gain crossover frequency you need to find out. At that gain crossover frequency, so you will find the phase, then you will find the phase margin. Okay. So you can see here this is your 0 dB. So 0 dB line means gain equal to 1. So when it is crossing at this point, because this gap is 1 decade. In 1 decade 20 dB is reduced, so it will come to this point. This asymptotic plot exactly. Okay, so it implies that the omega g gain crossover frequency is 1 radian per second. Okay, am I correct? Can you understand these things? Can you make comment please? Okay, I am waiting for your response whether you are getting or not. So this omega g you need to calculate first at which frequency gain will become 1. So here we are getting omega equal to 1. Now we need to find out at omega equal to 1 what is the phase, approximate phase. That phase you need to calculate. Okay. So what is the phase? Can you calculate the phase? So this phase would be, so denominator is providing 0 degree. So this one will be minus tan inverse omega by 0.1 minus tan inverse omega by 1 minus tan inverse omega by 10. Okay, these three. So these three, okay, they will provide the phase. The corresponding phase I have considered, and I have considered minus sign because they are poles. Now if I put omega equal to 1, who will contribute? So this will become 1 upon 0.1 means 10. This is 1 upon 1 means 1. But this will become 1 upon 10 means 0.1. So this is almost 10. Tan inverse 10 means almost 90 degree. So approximately I am considering. This is tan inverse 1 means 45 degree. And this is tan inverse 0.1 is 0. So what is this phase? So phase will be minus 135 degree. So if phase is minus 135 degree, so what is the phase margin? Can I calculate phase margin? Phase margin would be simply, I have said 180 degree plus 5. So from here, what is this phase margin? So 180 degree minus 135 degree means 45 degree. So 45 degree is the phase margin. Okay, I think the question was the phase margin. So answer is phase margin is 45 degree. Is it clear to all of you? Yeah, you are correct, Joy. This is 45 degree. Fine. Okay. I think I can stop here because this is almost 1 hour. Okay. I may discuss more problem. Especially I was thinking that I will be discussing some compensator, phase lead, phase lag compensator, and what is the maximum phase, everything that will be discussed. So I can make one video for that later on, so you can follow that one. Okay, and if you have any confusion, please let me know in the comment section. I can make certain videos for you. Okay, and if you think that this is useful video, please just press the like button. That's all. Thanks for watching. Okay, do you have any question? If students are there, then I can discuss few problems on compensator. Do you want? Some students are there. I may continue for another 15 minutes or 20 minutes. Okay, so if you think that okay, so you will continue, no? Okay, let me then discuss few problems, more problems. It's not like that. So I will be discussing few problems on this another topic, state variable, but time is not there. Today I will not discuss state variable, but at least phase lead, phase lag, all those things I will be discussing. So can you solve this problem? So this is the problem regarding the compensator. The GCS is mentioned as K times S plus A upon S plus B. So what is the condition that this will act as lead compensator? Okay. So lead and lag compensator defined by simply phase. Right. So what you will do? So here in this case, so I can consider this one. Little bit like this. So K into, this is GS or GCS is K into S plus A upon S plus B. So where are the poles and zeros? I have one zero at minus A and pole at minus B. I am assuming that B is larger. Okay. Now just what I want to say that consider one point A is equal to j omega, then find out the phase contributed by this one and this one. So total phase, so you can see that GC of j omega will be k times A plus j omega, and this is B plus j omega. Okay. So what is the phase? Phase equals to tan inverse omega by A minus tan inverse omega by B. Correct? So tan inverse omega by A and tan inverse omega by B, this phase, if this phase is more than 0, it is a lead. If this is less than 0, it is a lag. If resulting phase is positive, then it is called lead compensator, and if resulting phase is negative, it is called lag compensator. So when it will be positive, so for positive means, because condition was that when it will be lead compensator. So if this angle is more than this angle, then it is a lead compensator. So omega by A should be tan inverse omega by A. This angle should be more, means omega A should be very closer to the origin compared to the B. Then it is actually lead compensator. Okay. Meaning is that I can say that omega by A, I can write here, it should be more than omega by B. That imply A less than B. Is correct. If A is less than B, it will give you the lead compensator. Good. I think it is fine. You have got the concept. So this was the problem, you can see. Fine. So the answer A less than B, the answer A is correct. Okay. Let me discuss different problem. Not this one. This one. Can you solve this problem at least? So this is one phase lead compensator they have said. Now we need to find out maximum phase shift provided by the compensator. Right? So what is this? So GCS is 1 plus 3 TS upon 1 plus TS. Okay. So what is the phase? Well, here we can find out GC of j omega, that you can do, and from that you can find out the phase. So you are doing these things. So it will be tan inverse 3 omega t by 1. This is for 0, and for pole it is tan inverse omega t by 1. Is it correct? So this is the phase. Now how to find the maximum phase it will provide? So for maximum minimum, one technique is that you need to take derivative of this phase with respect to omega. So at one frequency, if this phase, derivative of this phase is becoming 0, you will have maxima or minima, right? So now you can see that initially this magnitude will be more. So initial phase will be positive because compared to this one it is more, but towards the infinity, as omega is approaching to infinity, both will become 90 degree. So 90 minus 90 is becoming 0. So both will start from 0, again both will end at 0, this 90 degree. So initial phase is 0 degree, final phase is also 0 degree, but in between you will get some positive phase. That's how it is a phase lead circuit or lead compensator. So I need to take derivative of this one, d phi dw. So what is this? Tan inverse x, its derivative is 1 upon x square. Okay, so 1 upon 3 omega t, that square. Then again derivative of this 3 omega t. So with respect to omega, it will be 3 omega. Is it correct? Okay, minus tan inverse, again its derivative will be 1 upon 1 plus omega t, that square. And that you should make it 0 for maximum or minimum. So what is this? So 3 omega upon, I think, sorry, 3t was there. I forgot this thing. 3t should be there and it should be again t. Sorry for this. We are taking derivative with respect to omega. So this numerator is 3t, it is t. Okay. Now if you make it 0, so what you will get? Okay. So we can consider this thing, the total phase phi d phi d omega is 3t upon 1 plus 9 omega square t square. This is minus t upon 1 plus omega square t square, and that should be equal to 0. So we can solve for this one. 3t 1 plus 9 omega square t square equals to t times 1 plus omega square t square. So tt will cancel out. So this is a 3 plus 3 omega square t square equals to 1 plus 9 omega square t square. Is it correct? So if you solve it, it will be 2. So 3 minus 2 is 1 is 2, and this is 9 minus 3 is 6 omega square t square. So from here, so this is 3, so omega square t square equal to 1 by 3. Is it okay? Right? So what you will do? You will consider this thing, this phase. So at this frequency, so at certain frequency omega, so omega square t square equal to 1/3, then only you will have the maximum phase. Okay, so can I calculate then phase? What is the maximum phase? Phi max. That I need to calculate. So phi already you have considered tan inverse 3 omega t minus tan inverse omega t. So omega t, I have got this thing that omega square t square equal to 1/3. So omega t equals to 1 by root 3. So what is the maximum phase? Is tan inverse 3 into 1 by root 3 minus tan inverse 1 upon root 3. Okay, so that will give you tan inverse root 3 minus tan inverse 1 upon root 3. So this angle is 60 degree, this is your 30 degree, so it is your 30 degree. Is it clear? So any confusion, please? Okay, I think you have got this thing. So I'll stop here because I need to stop here today. I'll discuss more in future videos. Okay. So if this is useful, please just press the like button. Okay, I'll continue. I'll discuss more problem in next videos. So thanks for watching.